Okay, everyone. So let's begin our final session. This session, Joonsuk Jung from Yonsei University QIYA will be presenting about decoding across LDPC codes. So let's invite our speaker.
Okay, good evening, everyone. I'm Joonsuk of Yonsei University, and I'm going to talk about how to decode across LDPC codes. This presentation is advised by Professor Choi Park of Yonsei University. Uh, I'll be talking about how to perform quantum error correction and how quantum error correction codes has gone so far. Let's start with classical error correction. A basic example of classical error correction is the repetition code. Our classical binary data may have bit flip errors where 1 goes 0 and 0 goes to 1. To prevent this, we repeat the ones and zeros to make it fault tolerant. Here, you can see that our code words gets noise and decoded by the majority vote. Detection of the errors is done by the parity check matrix. The parity check matrix is a matrix that gives a 0 when we product the code words like this. This means it has all the code words in its null space. When the parity check matrix is multiplied to some noisy codes, it gives a syndrome like 1 or 0, 1. The tenor graph on the right gives visualization of how it's done. The squares are the checks of, which are the rows of the purchase matrix, and circles are the bits of the purchase matrix. So the error correction code gets robustness that increases as the size of the code increase, where you can see in the left. But if the physical error rate is very high, the error correction code, error correction system fails. The example on the bottom is the logical error rate plot of a classical repetition code, where you can see the threshold is about 50%, which is quite reasonable because it is 1 and 0, and the decode is majority vote. So that was the classical error correction, but things get a little bit complicated when it goes to quantum. Because our qubit has two types of errors, bit flip errors and phase flip errors, the error correction code must be able to detect both errors simultaneously. We need measurements that doesn't change the observable, which we call the stabilizers. The stabilizers gives parity checks, which are called syndromes, where you can see here, the stabilizer is projected on the states, and we get the state is preserved, and we get a syndrome, which is plus or minus. The overall process of the error corrections looks something like this. We get an error, and we measure them with X and Z stabilizers. And from the measurement, we get syndromes X and Z, which we decode with decoders and make it error correct. Lastly, we do error correction. This example here is the process of minimum weight perfect matching decoder on a toric code. The toric code, this is the toric code's tenor graph, which you can see as it has a plane of qubits and X and Z measurements. And the minimum weight perfect matching decoder gives a threshold about 10.3%. I'm not going to talk about the details right now. So that was the quantum error correction. Okay, we'll go to the how to decode QLDPC codes. Before moving on to QLDPC codes, we give a formal definition of the error correcting codes. All the classical codes are binary linear codes, which are defined right here. The dimensions of the classical code is given against the rank of the parity check matrix, which means if we have a low rank or low density parity check matrix, we have more dimension, which means a logical qubit can present lots of states. Okay. And the distance is defined as the minimum distance of the code words. And in the quantum code, we have, you can see it right here, the HX, which parity check matrix X and parity check matrix Z is orthogonal. And the other parameters are defined as follows. So we have the definition, but how do we construct a quantum code? The construction is done by hypergraph product. The hypergraph product looks like something like this. We get two classical codes and we get a product and we get a quantum code. The quantum service code is made of two repetition code and quantum toric code is made of two ring codes, which is classical. The details are like this. I'm not going to see about the details. This brief explanation. We product the rows of the classical code and the columns of the classical code to make it orthogonal to each other, X and Z. So our main topic, quantum low density parity codes. The low density is, as I said, the low density parity check codes. QLDPC codes is where each qubit is connected to a bounded number of qubits. The toric and surface codes are the QLDPC codes with qubit degree of 4. The qubit degree means that each qubit had 4 stabilizers connected to each other. For a long time, toric code and surface code was close to the state of the art, which was the overhead about 1,000 qubits. That was the main problem of the toric and surface code. But recent development in hardware made it possible to have long-range connectivity to make QLDPC codes with much less overhead possible. And the recent research had the overhead about 50 qubits. Also, the strength of the QLDPC codes is that it has lots of platforms supportable for the QLDPC codes, like neutral atoms, ion traps, photonics, and superconducting qubits, which are the main platforms. So we have the family of QLDPC codes where you can see right here the Kitaev toric and hypergraph product and others that I really don't know. As you can see, the dimension and the distance order comes together, which means linear overhead for the size of the code. So we have a great QLDPC codes, but how to decode them? That is the BPOSD decoder gives the general solution to this problem. First, the BP belief propagation is a general decoding algorithm for classical LDPC codes, which can be applied to any tenor graph like this. The strength of BP is that it is extremely fast, which runs in linear time. I'll show briefly how it's done. First, we set the belief for each bits according to the prior knowledge that we have about the error rates. Second, we perform a propagation via the code of telegraph. The propagation is referred as messages. This is the implementation of a message passing algorithm and product sum variant. We propagate the messages according to these rules. As you can see, we set the beliefs and propagate the messages, and finally get the output. This works quite well for linear LDPC codes. But if we do it on the toric code, the results look something like this, where you can see that the distance increase as the distance increase, the logical error rate increase, which is not a working decoder from our previous insights. The problem is the trapping sets. The trapping set is usually occur in all various QLDPC codes because of the cycles that fails to convert to a solution. As you see in the animation, we set the beliefs and propagate it, but that doesn't converge to a solution. So for QLDPC codes, we need a post-processing method called order statistics decoding, OSD in short. So the OSD is a post-processing routine that always returns a solution. This is the overall process. We input the syndrome and we have a BP output. If the BP output is true, we just use it. But if not, we use OSD to get a right solution. The point in using OSD as a post-processing method is that BP gets quite a good solution, where you can see that where we have seen that BP gets a quite good solution. So we use OSD. How do we use OSD? We use BP output as a light decision, which means the BP gives probability that it gives a good solution. And we discard the low probability qubits and get a full rank sum matrix. The full rank sum matrix always has an inversion, so we can get a direct solution for the problem. So the BP applying to the toric code, we can get a working decoder right here, where you can see the distance increase as the distance increase, the logical error rate decreases, and we get a threshold of about 9.4%. The detailed parameters are like this, and this is in the Python package called QLDPC, so you can see through. So that was a BPOSD. I'd like to point out some discussions where first, what are the bottlenecks of the BPOSD? The BPOSD's bottleneck is the processing time of OSD, which takes cubic time according to the block length. Hopefully, BPOSD gives since BPOSD gives a general solution, hopefully we can find a much faster local solution for other problems. And the second question is that can quantum error correction code be done by, can be the solution for FTQC? But this is not quite true because according to the theorem below, we know that implanting universal gate set is challenging in general. So we need other methods like magic state distillation and T-gate sorts and sorts. So that was my presentation. And for this vacation, I'll be reviewing the things that Google has presented recently. So anyone interested, this is my LinkedIn, so contact me. Thank you.
Okay, so if you have any questions, please feel free to ask.
The error mitigation is about the hardware, I think. It gives, I don't remember all the details, but it is not not the core of the quantum error correction. The quantum error correction code is the core of the error correction. The mitigation is subroutines, I think. But doing error mitigation is quite good because where you can see that we have a threshold. The threshold is the point where our quantum error correction system fails. So we have lower physical error, then we only have to use little bit of qubits to make a logical qubit. So yes. Any questions? Yes. The BP will converges in a linear quantum circuit, so that is not the case for the quantum, because if we have a linear code, then the density will be quite high, saying that the connectivity will be 1 or 2. Yes, but I believe there is loops, then there's no guarantee that BP will converge. Yes. Those quantum circuits does have loops. Yes, so we yes, that I think there will be some other local solutions for using the BP, I think, but I don't remember. So thanks. Yes, I think it's quite good because of the speed, but yes. But also there are both BP LSDs and BP. Yes, I don't remember. Sorry. No more questions, then I'll stop right here.
Okay, let's thank the speaker again.
Good afternoon, everyone. My name is Choi, Seokwon, undergrad student in physics, Department of Physics at Yonsei University. And also I'm serving as a vice president in QIYA. And today I'm going to present my topic, the future of HHL algorithm through recognition system models. In this presentation, we'll start by explaining HHL algorithm is, and we are going to talk about examples of HHL algorithm, the recommendation problem. And finally, we conclude with a discussion followed by appendix. And from now on, I'm going to explain what HHL algorithm is, but I'm not going to explain deeply because of limited time. HHL algorithm has given name because Harold Hasidim Lloyd made this algorithm at 2009. This is algorithm to solve linear system of equations, and that is a method to find x on ax equals b. To solve this in a quantum system, we transfer this as a quantum model, and we utilize QPE like as a subroutine and get an exponential speed up from that. And I'm going to introduce example of this as I'm going to explain the usage of example as a recommendation problem. The recommendation problem is about recommendation system. It suggests products to users based on past purchase ratings of products. The recommendation system makes suggestions about products to individual users. By analyzing these patterns, we can approximate the preference metrics from existing data and make predictions for similar users. As an example shown in the PPT, like Netflix, when you add a movie like To Kill a Mockingbird, if you have seen it, the system groups you with some types of similar users. Based on this grouping, you recommend similar movies like the shown in the picture. So our problem is simplified as getting an approximation of the preference metrics and suggest other people like a same type as a recommendation. The insight of recommendation problem is define a preference matrix T, which is epsilon close to original matrix. And we predict this data. And based on previous studies, approximating in low dimensions will be used. For this, we define T as a M times N matrix, where the entries represent user product preferences. And we produce this data into specific vectors for further analysis. And M represents the number of users, and N represents the number of products elements in that matrix. Just like the projection on the right side of my PPT, you can see that from rank KR space, we extract sigma 1 to space KR only. Like you can see the arrow projection over there. We just extract for the things we are going to use in the recommendation system. Okay, then I'm going to explain the quantum algorithm to use recommendation system. Yeah. In quantum algorithms from prior research, we use the theorem projection onto one sample, AK is close to projection onto itself on AK. This is where therefore low rank approximation like I discussed before can be efficiently achieved using sampling methods underneath my PPT. By defining a samplist matrix AK, which includes some scaled entries from original matrix A, then we can achieve similar results without significant loss of accuracy. The sampling layer enables the first computation by focusing only on relevant elements. Like you can see the 111 over there, and we just extract what we need for the approximation and amplifying like the blue color at there, like following the sampling rule. And by applying low rank approximation of sample following and the sampling techniques discussed earlier, we can effectively approximate the preference metrics in recommendation systems. The results quantum state corresponds to a row of the sampled metrics representing a user's preference, which enables to make accurate recommendations. And from the binary research tree, like state preparation could be done in polylog m and time. This is shown in appendix, and you can see how it works, but I'm not going to explain this because of limited time. Okay, from method of projection, like I discussed later before, what we need is a projection of sample of single values in the interval. Using HH algorithm, which solves the system of linear equations, can be used to estimate the single values by performing the mapping. Because it estimates sigma value lies on the table, like shown there. For projection, the HHC algorithm helps to estimate single values by mapping, and where sigma I was in a specific range. This allows us to project the sample data efficiently, achieving accurate approximation in the polylog m time of a epsilon. You can see the algorithm follows on this diagram, like sampling, rounding the professional matrix and sampling there, and we can solve the quantum methods using quantum singular value. Okay, to quantum, the probability that this algorithm produces a bad recommendation can be calculated using the given formula. So in order to work in practice, there are the threshold defined as epsilon, and this is shown in the previous paper. And we have to define kappa equals 1/3 to work in practice. And therefore, the algorithm runtime could be like, we discussed the polylog m times later before regarding the method of projection. And we just add polylog k. So the total runtime would be poly k polylog m time. By inspiring this, we can think of quantum-inspired algorithm using classical computers. In a quantum-inspired recommendation system, we are going to introduce some methods to, like we sample data and we extracted eigenvalues from there, but we are going to change it in classically. A quantum-inspired approach uses different sampling instead of complex quantum computation. For example, a KFB algorithm approximates the matrix M by sampling rows to N, such that N transpose N is close to M transpose M, and A transpose N span to column space. And a modified version uses the L2 norm sampling based on single values, enabling a probability distribution proportional to the squared probability norm. This gives a probability regarding to the singular value vector, like you can see from the PPT down there. One goes to probability there, like on the steering the graph, and you can see. So in a quantum-inspired recommendation system, a sample of S rows a matrix A provides good approximation to A, where D is the best low-rank approximation. And we can apply sampling rules both rows and columns, like just we did in the quantum algorithm, but we are going to sample the data and sample rows and columns. You can see from the diagram over there, you can extract data from sample rows and columns. We following the sampling rules over there, we can make, like, if the data is million times million, we are going to reduce this as constant times. Like, if you get a million time million all the data, we are going to reduce this dimension to constant time, like 5 by 5. So this, using this method, computing this will be very easy. So projection is computed by determining the top k singular vectors. Like, we are going to extract and we are going to project in classical way. So U1, U2, UK, so the column column space of W. This is spanned into row space using VT, like VT and VT times VT transpose. You can think of approximation project vector like over there. And the probability of failure is about 1/10, but this takes very much of mathematical methods. But if you want, you can see on the paper. So the total diagram of quantum-inspired algorithm is, you can see like quantum algorithm has you have a same rounding process, but unlike the metric sampling that quantum algorithm has, we have a L2 norm sampling, like the Frobenius norm, and you can get a constant size of sample. Like we tried to reduce the calculation, and we have a classical SVD from there to find the approximation. Unlike the quantum algorithm, just quantum system to find the eigenvalues. Okay, and this is my explanation about quantum algorithm and quantum inspired algorithm, and we are going to discuss about this. I'm going. I have to explain the quantum inspired algorithm one time, because it takes only poly k time to rounding, and we get a log mn time to get a method. We just have a polylog k log mn time, and this is only polynomially slower than the quantum algorithm. Regarding quantum computers in practical deviations, we can think that this algorithm works pretty well. Okay, the total runtime of the quantum-inspired algorithm was only poly k log n time, and which was slightly slower than quantum algorithms. This raises us the question: does HHL still offer a quantum advantage? In classical method, the same rounding process is applied to preference metrics, but L norm sampling and classical SVD are used instead. In conclusion, if the entire algorithm can be simulated on classical computers, any problem solved on n-qubit quantum computers can be resolved only within poly n time. This implies PQP equals P space, making quantum computers nearly obsolete. Therefore, while we believe HHL offers exponential speedup in theory, more practical research is needed to validate its real-world utility. This was why I think it ended faster than I expected. This is my presentation. If you have any questions, feel free to ask. 이런 방법 말고도 다른 컴퓨터 스파이들된 알고리즘 그거는 제가 조사를 잘 못해서 제가 조사한 바로는 네 이렇습니다. 그래서 사실 이렇게 되면 저희가 양자 컴퓨터를 쓸 이유가 없어지죠. 근데 저희는 그렇지 않기 위해서 다른 노력들을 해봐야 되지 않나 또 하는 생각입니다. 네. 네, 그렇게 생각했을 때, 그 말씀하신 게 뭔지 제가 잘 모르겠는데, 스페이스 매트릭스가 뭔지 좀 설명해 주시겠어요? 네, 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 그러한 고전 수학 테크닉이기 때문에 퀀텀 인스파이더라고 볼 수 없다라고 말씀하시고 싶은 거예요. 네, 그, 네, 잘 모르겠습니다. 다른 질문 있으신 분 있나요? 쓰시다면 이쯤 발표 마무리하도록 하겠습니다.